little bit of a preamble and draw some pictures for people so everyone can get some context for why this problem that both Formalized and Crim are trying to solve, and a variety of other people in the ecosystem, is so important for really like the AI industry at large, but for Bittensor specifically. And that problem is how to train models in a collaborative sense across the wide internet and under incentives. So Bittensor already has a pretty decent set of training mechanisms, 9, 29, 37, 21 subnets that are training machine learning models using incentives. But the difference between the holy grail of distributed training and what we're referring to on this call, the difference is that on Subnet 9 and 29, there's no collaboration between miners. Every miner model is a unique team. And with the exception of the occasional model merge that occurs, or like teams that take other models and add layers or add new parameters to the model, there really isn't that much collaboration. And the holy grail is, how do we incentivize compute from across the globe to coordinate together and train a singular model? One that, if I bring an H100 and you bring an H100, Karim, and Formalized brings an H100, we can have 3 H100s working on the same model rather than each of us training independently. Now, Bittensor has both of these mechanisms running right now. So, Karim, we're going to talk to you about Distry, which has been going for, I think, about a month and had a fair amount of progress and success. And we're obviously going to be jumping into that in a second. We have both of them. And it's great that we have both of these types of mechanisms at play, because we're ensuring that no matter what the end result is, we're going to get something good. So the importance of distributed training, I'm going to go ahead and draw it out for people on my screen for why this problem is so important and how we're going to approach it. So y'all can see my screen. You're looking at my Miro. Let's go through some components here. Here's my nice, beautiful drawing of the Bittensor blockchain progressing beautifully through time. No halts, no downtime, never a hotfix required. And we have here 3 subnets with their incentive landscapes. I think this is subnet 4. And then inside of these subnets, obviously we have miners and validators, and they're setting weights and setting the incentive mechanism. And this is, Bittensor's extremely abstract design for building a variety of different types of mechanisms. Now, the distributed training problem, why is it so important? And why is it the holy grail? There's only X, Meta, OpenAI, NVIDIA, that individually have the GPU power, or prowess, you might even argue, to train foundation models, the things that underpin, Chat and Claude, to the size that is required to get the type of intelligence out to the world that people really appreciate. So like Claude and GPT-4, these are foundation models in the hundreds of billions of parameters. And Subnet 9 and 29 are pushing the limits of what's possible with their training mechanisms. But there's no coordination between those miners. There's no coordination between the compute. And the holy grail of distributed training, it's actually a problem I've been focusing on for, Bittensor might have been even invented in my mind to solve this problem. How do we coordinate the compute to train one model collectively and have that model rival in size from a foundation size, a language model that's 100 billion, 200 billion, 300 billion, 400 billion, trillion parameters, training for months. So a bit of a side. So let's go through like the steps of producing a model that you use for ChatGPT. So there's 2 steps: effectively pre-training and fine-tuning. We're not going to talk about fine-tuning. It's actually less of a computational problem. It's more of a skill issue, fine-tuning, about collecting data for RLHF, doing reinforcement learning. coalescing the model that we're going to first pre-train. And in order to pre-train a very large language model, we basically take an infinite corpus of unlabeled text that comes from the web, usually from Reddit, from Facebook, from Twitter, from the common crawl, terabytes and terabytes, thousands of, trillions of tokens. And we compress it into the weights of a language model. Llama did this recently with their 405 billion parameter model, which they released, their 70 billion parameter model that they released. And they used 16 trillion tokens. That's multiple terabytes of data. And they had to compress all of that into the parameters of that model over weeks and months of training, depending on the size. And they use a lot of compute to do it. And the training mechanism is actually very simple. Pre-training is like the simplest training mechanism, because effectively all you're doing is it's self-supervised. You take a sequence of text and you feed it through your model, and you try to predict the next token, and you use the next token prediction logic probabilities and cross entropy to back propagate through your model and update the weights slowly, iteration after iteration, until you converge on the ability to basically predict your data. I like compression as a good explanation for what this is doing. The 405 billion parameter model has remembered all of the information in the web that it's got from its incredibly large data set. And this process takes months and a lot of coordination. So I want to show you guys this image right here. So this is maybe like, these are H100 pods. I've drawn my H100 pods. This is 1, 2, 3, 4, 5, 6. I think it's about 32 H100 pods. I'm going to do the math here. It's like 256 H100s. So Meta trained on 16,000 H100s, which is 62 times the size of this. So if you can imagine a cluster of H100 pods 62 times larger than what I'm showing you on the screen. I did actually draw it out once, all 16,000 H100s on a Miro board, but it crashed Miro, and I thought that would be bad for this presentation. So I've just gone ahead and drawn this, which is, as I said, this is 256. So in order to train a 405 billion parameter model on 256, not even 16,000, 256 H100s. Each one of them needs to pull from the data set. They need to distribute their 405 billion parameter model across the H100s. So they don't just run it on one H100, they actually split it 8 ways. And indeed, in Meta's paper, they split their 405 billion parameter model across multiple nodes, where the 405 billion parameter model, when you did a forward pass, it was literally running in pipeline parallel. So it wasn't just pipeline parallel, it was context parallel, tensor parallel, and data parallel training. So the 405 billion parameter model was running across many of these nodes. And then when it did a forward pass and a backward pass a number of times, the batch size that it was required to produce an update, it would communicate an all reduce operation with all the other nodes in the network and run an update. Now, it just seems like simple math for people to understand, like the real size of this problem. So a 405 billion parameter model is like at least 100 gigabytes. And if you have 256 H100s in here, this is about 1, 2, 3, 4, 1, 2, 3 by 3. It's about 9. Let's say there was 9 replicas, and then times 64, right? That's 576 nodes that would need to communicate 100 gigabytes of data in order to update their model every step. We can do the math here. 576 times 100 gigabytes. It's 57,000 gigabytes of data, or 57 terabytes of bandwidth requirement in order to do a single gradient step of the entire model and update all of the parameters. Now, in practice, if you read the Llama paper, it's an absolute masterpiece in engineering you'll understand that they do have a lot of tricks in there, that they don't need to communicate all of the parameters with everybody at every step, and they're doing compression. They're not actually sending over the wire the float 32 parameters. They're doing compressions down to even maybe 1-bit compression to communicate the gradients. But at the end of the day, it's a gargantuan problem. It's a very difficult engineering problem just to coordinate this amount of compute and have the bandwidth and compute requirements and the data requirements to train a model that is significant enough to be at the top of leaderboards, rivaling GPT for any reasonable benchmark. So I mean, holy shit, it's a mouthful. I recommend Formalize. Could you do me a favor, actually find that paper for me and post it into the channel, the Llama 3 paper that the one I'm referring to.
Yeah, I'm getting up.
Okay,
heard of llamas.
Yeah, great. Very huge. All right. Well, the holy grail of distributed training is, well, hey, what if I had an H100 and you have an H100, and we can all coordinate and work together and combine our H100s and somehow train a model like this without requiring llamas, government scale, Manhattan project scale compute cluster that only a couple companies in the world have available to them. What if we could do this in a collaborative sense? Better yet, what if we could do this in an incentivized way? And I think this is the clutch piece that a number of people have been missing for a very long time. I've been talking about this for a very long time, and I worked closely with the HiveMind team in 2019, and I told them, guys, we need incentives. And why do we need incentives to make this kind of thing work if we're going to try to coordinate a bunch of people to work together? It's just that this is very expensive. 256 H100s, guys, that's like tens of millions of dollars per month. And not only that, but if you want to coordinate these people, what we've learned at Bittensor is that one of the best ways to do that is to craft the problem as an incentive problem. Different things arise. You can guarantee if you can craft the incentives properly, you can guarantee that the miners are bringing the right type of compute, because that's the way in which the incentives are aligned. Hey, you can't run from a 4090 on your desktop computer. You actually need an H100 box. And we've seen that across a number of subnets on Bittensor. We can't force the miners to get very sophisticated and to bring a lot of hardware. You cannot do this with altruistic computing. You need some form of incentivization to really scale. And that's something that Bittensor has in spades, right? We have the technology. We have the technology to build this out. But the question remains, how do you even do this? Especially over wide internet, where there's many participants not in the same data center. They could be in different continents across the globe, sharing gradients, 100 gigabyte size, with wide internet connections. A lot of work needs to go into how to reduce bandwidth. And so a couple of weeks ago, I was on a call with Macrocosmos. We were talking about this problem. We were talking about different kinds of compression methods. And there are a variety of different approaches from the open source community. One just came out today called Photon, about reducing the bandwidth considerations. And a lot of those techniques rely on the idea of either allowing the models that are distributed across the internet to train locally, do a lot of local steps on their model before they communicate gradients, or to communicate less information per step. So do a compression of the model and only communicate this compression. So there are a number of methods. DLoco, Cocktail SGD is famous. Distro is proprietary; it's under NDA, but I believe we know what they're doing, and all of those can work inside of Bittensor. But in order to make it work, we need to craft them differently. They're all built for kind of this idea that comes out of the research community, the academic community that money should not be involved, and the academics don't like economics, and they don't like this idea of competition or adversarial behavior. But that's, hey, we were born in the darkness. We know these things as primaries. So we've taken, and by we, I actually am referring to Karim on stage and Formalized on stage, some of these methods that are all about compression, and crafted them in such a way that we can frame this decentralized trading problem as an economic market that can work on top of Bittensor. So without further ado, hopefully that was a good preamble. And if there's questions, people can ask them in the chat. I can see if I can answer them. Without further ado, let's talk to Karim and Formalized about how we're doing this. Great, guys.
Hello, amazing. I'm not sure. Maybe I can. Maybe a good the sort of setup you gave me consists to share a bit about how we're doing it on Subnet 38, and then I can hand over to Formalized how he's tackling it himself.
I think that's perfect. Yeah, give us a breakdown of how it's working on 38.
Yeah. Let me share my screen.
All right, Karim, we're good. Let's go.
Cool. Let's go. So the way, I guess, very good intro, Cons. So I think the way we're tackling it at Subnet 38 is mostly focusing on the first part you mentioned there, Cons, which is delaying how often we have to share this huge model size. And so the way we do it at Subnet 38, thanks to Bittensor's great subnet mechanism, is we have just two simple synapse calls. The first is a train synapse call where a validator sends a random layer, chooses a random layer of the model and sends that to the miner. The miner has a local version of the model that it trains on, and it picks a random subset of a global data set, and it trains on that subset of the data. It then sends back the gradient for that random layer that the validator asked for, as well as the subset of the data it trained on. And the validator retrains on that data set and compares the gradient it's calculated locally versus the gradient of the miner. But because we're only picking a very small layer and a very small part of the model, it doesn't have to redo the entire amount of the work. It just does a small subset of it. And so this is a way for it to kind of validate that the miner is doing and training as it is claiming to be training. And then it keeps a global unified track of how many data points, how many gradients all these miners are training on. And it then waits until we hit like a global batch size. For us, we use a very large global batch size, and we're able to delay how often we have to sort of average gradients or all reduce, because we use an optimizer called LAM that enables us to not just use like 256 and 512 batch sizes, but batch sizes up to 64,000. And so we're training as every node typically does in a normal environment, and this very expensive, time-consuming all reduce operation only happens every 64,000 steps. So once we hit those 64,000 steps, we send a different type of synapse call, and that's an all reduce synapse call. And I think we can maybe go into what all reduce, how all butterfly all reduce actually works. But I guess for the purposes for people who don't want to dive too much in the technicalities, effectively what all reduce is doing is, imagine every single miner has trained using the same model and gathered a number of gradients. All reduce is effectively an averaging operation. So Const's miner averages with mine, with Formalized, with everyone else there, so that we all have a single unified average of those gradients. And once that's the case, we then apply those averages to our model and update the weights using the same optimizer to get to the new model step. And effectively, we've just gone through one iteration or one step or one update of the model. Now, our validator sends this synapse call and gets all the miners and joins the miners in running an all reduce. And through running the all reduce can tell which miners have succeeded and failed in this averaging operation and penalizes them accordingly. Now, as Cons mentioned, all reduce is very highly dependent on bandwidth. And so we also have a proxy method for evaluating bandwidth by asking miners after they've done the all reduce to stream parts of their model and timing how long it takes for them to stream their model to get a proxy metric of their bandwidth, which is highly correlated with whether they'll succeed or not with this all reduce. And once this all reduce operation terminates, the validator has every node has the same new model state. But just in case anyone's failed, the validator will upload that model to Hugging Face so that any miner that's failed can pull it back down, or any new miner that's joining at this step can pull it back in. And then we go through the loop over and over again. We train, we hit the batch size, we all reduce. Anyone who fails reloads the model, and we go over and over again. Now, this is a good system for small model sizes, but needs to be tweaked as we grow. But so far in the last 30 to 40 days on the subnet, we've done pretty well training on 250 million, 500 million, and I think live now on this Hugging Face dashboard, you can see we're training on a 1 billion parameter model. And if I zoom in a bit here, what's happening here is this is kind of like the baseline run of what would happen in terms of your model's loss if you were just training this model on your own, if you got a couple of H100s or just trained on one, but on the same batch sizes. And here in blue, you can see how our collective 250 miners are training on a single model. So we're performing quite close. Granted, it's a bit slow, but a bit close. So that's effectively how we've been progressing with this problem. And I'd like to say pretty well with a 1 billion parameter model that's been training and converging pretty nicely. And that probably maybe a good leaping off point to talking about this with constant distributed is this final slide here that talks about kind of what we are aiming for in our subnet. And that's like maybe a good way to visualize the strength of a distributed training system is through this pyramid. Maybe pyramid's the wrong analogy. Maybe you can think of them as 4 loops integrated. But effectively, what we care about with distributed training is sort of like a number of things. The first is the model size, and that's what we've been steadily increasing. If you're doing great and you're proving people are training, but you're only training on like 100 million parameters, 500, it's not that effective. We want to be growing quickly, and we want to be rivaling these big models that can be state of the art. And so, as I mentioned, we've jumped from like 250 to 500 to 1 billion, and we're hoping over the next couple of weeks, months, to be pushing the frontier of what you can of the model to the maximum size model you can have on a single GPU. So depending on how clever you get, we're talking 7 billion parameter model here. But once you're scaling the model size, the important thing is also how well you're converging. So can you bring the model's loss down from the likes of what we were seeing on the graph there of like the 10.8s to 10.9 loss you're starting with, down to low losses, low reliable losses, to effectively prove that you're training and that people aren't just feeding you garbage gradients. And then the third layer on top of that is how quickly you're training. So let's say you're upping your model sizes, you're converging pretty nicely. You also want to make sure you're not taking hours and hours and days and days and days to train. And at the moment, it's taken us 30 minutes to hit this global batch size of like 64,000 gradients and about 5 minutes to average them. And as we grow our model size, obviously this becomes more of a challenge because you're averaging bigger data, but we hope to keep our benchmark close to that and even reduce it a bit more. And the final cherry on top is like how decentralized you are, but this is, I believe, a nice to have at the moment. We've currently sacrificed a bit of decentralization for stable performance. And so we have one UID, master UID, that controls when we run this averaging operation, but we can easily see a world in the future as the system gets more stable that we have more UIDs that are capable of triggering this all reduce and even potentially miners in the future. So this is just like I guess a brief summary of where we were with, or where we're going with Subnet 38. Not sure if anyone has any questions, or maybe Formalized, I can hand over to Formalized as well.
So I want to say something though, Karim, because it might not seem that interesting to some that we're only training here a 500 million parameter model, but this quite literally, this 1 billion, right? But every time that you increase the size of this model, it is the largest incentivized, decentralized trained model in the world.
Exactly. I mean, I think up until Prime came up with what is I don't believe is a trustless mechanism. Even the state of the art in most papers you look at, I think if you look at, if I'm not mistaken, even distro were doing it just on the 1 billion. Maybe I'm mistaken. So I think we're very close there to the state of the art of what people were just doing in a trust-filled environment. I think that's a good distinction and a good reminder for everyone is, yes, in the normal world, we talk about trillion parameter models, but in the decentralized distributed world, 1 billion has kind of been the frontier for a while, and we're hoping to move past that very soon.
No, but specifically, Karim, it's not just decentralized. It is incentivized. It is trustless. It is incentivized, and it is decentralized. And those three things are required. And no team in the world has ever achieved it. As far as I know, I've never heard of a trustless, decentralized, incentivized model of any size trained whatsoever. And Karim is the first person to actually go and really do it and have a model that's converging. Now, look, we've got a ways to go here in terms of model size. As you said, we've got a ways to go in terms of convergence. We've got a ways to go in terms of adversarial resistance. Like, there is no doubt. But, really, congratulations, Karim, for being here first, and worthy of a variety of research papers. One of the questions I have about you and the design is how are you framing the incentive landscape so that we're taking advantage of Bittensor properly? So, like, in one perspective, it's like, how do you protect the network through incentives? And two, how do you drive people to bring more compute to the problem and lower the loss?
Yeah, it's a good question. So I think for the train signups, there's still a ways to go there, but we've basically picked it by allowing people effectively the way part of the reward calculation is based off of how many dataset indices you train on in the period the signups is sent. So effectively, the formula here becomes the more compute you can power up into your miner, the more dataset indices you can train on. And so there's a high correlation between the miners that are training on the largest amount of dataset indices and those with the higher incentive. And effectively, it's a two sides of the coin, and we try and balance it. It's compute and bandwidth. And so the other formalization of the reward score is how fast bandwidth are you providing? How much bandwidth and how much upload and download speeds are you providing? And the way we formulate that reward problem is after you run the all reduce, we load the model state you're loading through an RPC call that's opened up, and we time how quickly you're able to respond to that call and upload your model to our validator, a very small shard of the model. And we use that to guess how fast of a bandwidth you're providing. And the aim here is that both formulas will incentivize people to provide more and more compute, but also faster and faster bandwidth. And it feels like our theory is like that formula will enable the right balance of miners who can both contribute compute and then average it and share it with the rest of the network.
Beautiful. Karim, right now, do you think that the network can sustain more emission? Or like, is it sort of in this sort of low hanging fruit right now where the miners are not trying to destroy you? But if there was more emission, things could get a little wild?
Yeah, it's a difficult question to answer. As you said last week, right? Like, we don't have a test net. Like, mainnet is test net, and so that's why with all our calls to validators, it's been like a slow and steady increase in emissions. And I think with each increase, we spot vulnerabilities and we fix them. So I think we can sustain an increase, but not like in honest fairness, we want like a tripling size in our emissions. We want a steady, 50% increase, 25% increase. I think we can sustain. and that it's open to obviously debate and to experimentation and finding out as we grow. But we do have plans to improve and sort of strengthen up our validation mechanism. But yeah, as we've touched on, these are all theories as to what's a robust and tight validation mechanism. And we're experimenting as we go. Currently, our theory is with the subset of like 20% of the gradients we're testing, it's quite difficult for people. We assume it's quite difficult for someone to hack their way around training the data, but being able to recreate 20 to 30% of the right gradients. And that remains open to be tested even further.
Beautiful. We have Stefan on the stage.
Hey, I guess first of all, Kareem, congrats. This is a super, super cool design. Congrats on being the first in the world to do this. That's quite an unprecedented move. Amazing. Also, sorry if I'm a little bit late on catching up with the design here, but so I guess could you break down for me how does the validator actually verify that the gradients are correct? I think you may have just explained a little bit of this, but I'd love to hear a little bit more.
Yeah, sure. So it sends a random layer of the model to the miner, and it asks the miner to send back gradients, a compressed version of the gradients for that layer for each of the dataset indices it's trained on. And it recalculates, it retrains on a subset of the dataset indices the miner is trained on, and it recalculates them locally and compares the difference between both gradients.
What's the comparison method you're using?
At the moment, it's a simple difference in an absolute difference, but we're considering potentially moving to a cosine similarity very soon.
And
perfect. Go ahead, Steph.
Thanks. The follow-up for me is, I guess, what's the sort of ratio of samples the validator would need to train on to get a good estimation of the same gradient that the miner is loaded? Is it sort of 1-to-1? You're just doing sort of spot checks once in a while? Or is it possible for the miner to do a lot more work and train on a lot more samples, and the validator still has some confidence that their reference gradient is correct?
Yeah, exactly. I mean, that's the hyperparameter we keep experimenting with. At the moment, in each synapse call for each miner, we're testing about 10% of what the miner is doing. We found that, I mean, through testing on testnet to be a sort of very, very fine line, but it's a hyperparameter we constantly tweak. At the moment, 10% feels right in our analysis of what we're trying to see versus what miners are actually doing. And it's a hyperparameter we keep tweaking.
That is super cool. I know Jake has been scratching his head about this for a while, and we've had sort of a collegiate debate, you might say, about how much you can offload to the miners about this. But it sounds like 10% is a sweet spot right now. So congrats, guys.
Thank you. Yeah, it's an ongoing problem. I mean, I guess in a ways it could be incentivizing miners to try and be able to predict like these gradients well, but in a sense, I'm not sure to what extent, like them being like there's a maybe a hack, but the hack is probably the same compute intensive as just actually training on the data. So it remains to be tested and monitored and seen, and I think it's going to be an ongoing, unfolding problem to try and solve.
The accuracy here of the validation design is where all of the, in my mind, the gains can be made, because if we're just measuring raw compute and not something more in the direction of improving the model, we do limit the ability for the network to actually surprise us with improving. So one of the nice things about Subnet 9, obviously, right, is that we don't care how you train your model. We just care about the loss. And so the hyper focus, I believe that there is an outcome here where both these subnets actually sort of pale in comparison with improvements on 9 and 29, where the system gets better at allowing the miners to coordinate together or collaborate. We're sort of approaching the problem from different sides, right? So on the distributed side, it's like, hey, but we're going to force collaboration, and then figure out incentives that will make the collaboration work. Whereas on 9, there's no forced collaboration, but I know that on your team, Stefan, you guys are trying to figure out ways to allow different types of model merging to occur, and so we could actually see a kind of convergence between the running of the two types of networks.
Yeah, absolutely, Jake. We were pleasantly surprised and a little bit shocked when we looked at some of the models that the miners had uploaded on Subnet 9 and found that they've been very creative. They've figured out ways to take 7 billion parameter models and make them walk and talk like 14 billion parameter models. It's all quite genius. And I think the thing I'd highlight there is this is like a very, very early field in sort of pre-training, finding out how you can use a smaller pre-trained model and inflate it to look larger. I think it's a big engineering challenge, and the miners are the ones, fortunately, that are left to figure it out.
We have Autometa on the stage. Nice to meet you, Autometa. I know that you were brought here by Distributed. Welcome to the stage. Hopefully your mic works.
Can you hear me?
Yeah, we can.
It does work. Yeah, I have no idea what's going on. I clicked on a whim, and then the coolest conversation I ever heard was going on, and so now I'm on stage.
Well, great. So we have Karim Subnet. He's like Christopher Columbus for incentivized decentralized machine learning. And we also have Templar that launched, formalized here, heading that, which took the Kant design that we were working on for a while, that I was working on for a while, and has made it into a reality, and is running on Subnet 3 now. And when I was speaking to Karim recently, I was like, hey, we don't know if the field is going to go kind of like model slicing or lots of local steps like deloco. And I think that, we do need experimentation to occur. And so maybe this would be great to have Distributed talk about, Templar and the run that you currently have run it and going there. Samuel, do you want to come on stage?
So it's pretty interesting, as there's different ways to solve the problem, and we've decided to go with the very intuition that we can take a subset. We can have miners train on deterministic subsets of the data and broadcast this across the network, and have the validators it's almost kind of like what the does, where they reevaluate, because it's deterministic within that window. They can evaluate that miner's contributions and do a cosine similarity around it, and get a similarity score. Now, it's really interesting because we just started writing it. Then we still have some research going on that is kind of pointing at that there's a certain sweet spot for compression that leads to better convergence. So what does this mean? Is that it's a multifaceted beast, and there's loads of things to optimize for. And we wanted to constrain the surface area of our problem to just how well can you train? So in this subnet, it's about, for a miner, given your page, how well can you reduce the loss? So we fixed that by we don't do peer-to-peer, because I've worked in blockchains for ages, and peer-to-peer is peer-to-peer networking is another tail-ended beast that's not very performant, and we just didn't want to attack that. So by virtue of using S3 buckets, we offload all that. We offload a lot of the checkpointing, and we can just focus on, look, as a miner, what have you done? So we're measuring their share contribution towards reducing the loss. And so far, the current run, we seem to converge pretty quickly. But again, we just started. The incentives are not high, and the real tricksters from the ecosystem are not here. I'm not here yet, but it's looking really promising. It's still early days. Now, what we like about these about reason.
Wait, Samuel. So what are we looking at here? So just give some context. Yeah.
So this is a validator's loss after about 120 steps.
It looks like you need to make the run public. Formalize.
Okay, I will do. I'll do that shortly after. But yeah, this is, and we still need to sort out like getting all the validators on 1DB so we can see how they all converge. But this is just after about 120 steps. A step for us right now is about 20 something seconds. So, by focusing by just like reducing the problem to how well can we train in a distributed setting? We don't care about bandwidth, fix that. All we ask for is your raw compute. Now, there's some interesting limitations here, and it's a different kind of optimization problem because it being a global model, things like optimizer states and we don't average optimizer states, but by virtue of the validator mechanism, it's fixed. So we just what we expose to the miner is, okay, this is the system. You can't change the optimizer. Can you figure out how to drive this loss as low as possible? And so in the beginning, we can expect that everyone runs the base miner and throws more compute to it. But there's so much alpha in being able to understand the model architecture, which layers to train, and probably figure that out, because I trust like they're very give incentives, and the miners will come. Now, another interesting part of our run is that most optimizers are bound with learning rate schedulers. They're bound with you need to have a priori knowledge of how many tokens you want to run, and how many tokens you want to run, and how long your batch size and your token step. But we're using a WSD learning rate scheduler. So what this means is that we can train forever. But so in a WSD scheduler, you get a warm-up phase, then you get a stable phase where you train at a high learning rate, then you get a decay phase. But you can run this training phase forever. But once you start to decay, that training run is kind of over. But what we're doing to lend itself to Bittensor is that we're on a 1.2 billion now, just to warm things up. We can keep training that 1.2 billion model. Then every week, the team will just run the decay steps and post an eval. So even given the setup, not only is it distributed training, we're doing continual training, and even with a 1.2 billion model, I'm quite optimistic about where that takes us. And the infrastructure is ready to go to 10 bill next week. We just need to ensure that we've ironed out all the growing pains.
Yeah, so I would like to actually share the structure of the training run, because I think it's really quite interesting how this is being done and how it diverges from what Karim is focusing on. So we looked into the research and around distributed training, and we picked basically this novel type of distributed federated learning where you're sharing actual model parameters rather than gradients. So in our network, the miners are sharing slices, which is just compressed sets of indices from their models with everyone in the network through these S3 buckets. And so we chose this design because I think I mentioned on a previous call, it allows for there to be consistent bandwidth for everybody across the network. And also really fast upload speed between any server and their S3 bucket. So we don't need to worry about the specifics of one peer's bandwidth over another peer's bandwidth, which is always an issue. We have incredibly fast bandwidth, given the fact that these miners are paying for high bandwidth S3 buckets. The validation system, Karim, that distinguishes, I think, this design from yours is that the validators know which set of pages the miners should have been training on within a particular window of time. And then what they do is they also recreate a gradient, but they measure a cosine similarity between the gradient that's produced on the validator side after gossiping model states and the one that would be implied by moving towards the average of the model parameters for all the miners, removed just that one miner. So we look at the gradient step that the miner applied to his indices, and that by measuring the cosimilarity, so it's not exactly the gradient, it's very similar to the gradient. The way it works is, and we've studied this now, is that the best thing that a miner can do is actually train on more pages. So if they can produce a bigger batch size, they are going to have they're more likely to have a more accurate cosine similarity, or like a higher cosine similarity between the one that's produced by the validator. And so what this produces is an incentive landscape where the miners are really incentivized to bring a lot of compute to the network. Go and get an H100 pod, right? Go get multiples, because the only way that you can best approximate a sampled version of the cosine similarity is by training on the full sample of pages that the full set of pages that the validators are going to evaluate you on. So we've been focusing a lot on this really interesting intersection of basically an optimizer and an incentive landscape. What would it look like to frame a loss landscape in an incentivization regime, right? What's the isomorphism between lowering loss and trying to produce gradients? And we think we figured that out by basically casting this data set, like produce an update to the model that is in the direction of this massive set of data, and then have the validators sample from that set of data to reproduce that same direction. And this forces the miners to do massive training regimes, like produce massive training regimes across multiple computers. So that's one aspect that's really cool. And we think that, and we've already tested this on 1 billions and 2 billions. We're not up to 10 billion yet. That requires like torch run and FSDP and stuff like that. But this is a 2 billion parameter or 1 billion parameter formalized?
1.2.
1.2. You added a little 2.2. You added a little 0.2 there. Fun.
Just to match the state of the art.
Yeah. And also we have because we're sharing these slices, we've seen that like up to 1,000x compression is almost as good on with tests we've been working on with mostly CFAR right now, can be just as good as 100x and 10x compression, and sometimes even outperforms non-compression when doing all reduced between miners that are sharing just slices of their models, which is really promising. And if we can actually make this sort of incentive landscape work and the compression work at the same time, we think we have a pretty adversarial system to begin. High bandwidth, extremely high bandwidth, is using like probably the highest bandwidth technology you can find, and forces the miners to bring massive compute loads to the network. So I was watching this. I guess maybe this is even a little premature to have this call, because we just launched formalized just launched yesterday.
Yeah, yesterday.
On your birthday.
Yeah. Woohoo!
So congrats. Yeah. Anything else we want to share here, guys? Like, I think that these results are awesome, Karim. One of the slides that you put out here, I think really is the most important. I'm going to copy it and put it back into the chat. This right here is why I got into Bittensor. Noticing that compute requirements for Bitcoin and GPT-4, the Bitcoin was, what is this? 8 times, 8-fold, 9-fold. And we can bring that. Right, go on.
No, you go. I was just saying, I pulled these data just before we went on the call, so obviously we need to double check them. But obviously, that's the beauty of the landscape is, I think you've mentioned this a few times, Cons, right? Is it like there's so much compute there being or so much energy being directed to like Bitcoin mining, and you can see how much that like supersedes GPT-4's total energy consumption. So we have and I think already Bittensor is proving that we have the capability to sort of pool, because we don't need rival Bitcoin, we a proportion of that resource. So the question is just how to layer it all together.
Yeah, exactly. We have to capture it properly, though. And so, Karim, I hope that these two subnets have a holy alliance going forward, and everyone go mine Karim's subnet, but don't destroy it. This is super important for Bittensor. Autometa, pleasure having you on the stage. Any final things, Samuel, you want to talk about? Anybody wants to come on the stage, ask questions, talk at length of why this problem is so important?
This is a big deal. Everyone should be freaking out. We could get AGI out of this.
I agree. It's very hard to break the overtone window, Automata. Like, we've been out here in this field for a very long time. Nobody has believed that incentives needed to work at all in machine learning for a very long time. We went and built Bittensor to make it possible. And so here we are. Like, for me, this is a big deal to be able on stage and talking about this with these two guys. And yeah, right. Like, look at this image, right? 50 gigawatts, 447 gigawatts in terms of energy consumption. Like, if this chart is telling a story, it's telling that we could have GPT-5 on Bittensor, GPT-8, right? And more. And one of the things that I said to you, Karim, I think we should always be thinking about here is how do we not only craft the incentive so it brings compute, but how do we craft incentives so that intelligent people can actually speed up the training mechanism? And forcing everybody to run with the same optimizer, for instance, is not something that we have, right? So on Subnet 3, every node has got their own optimizer. And the network is actually completely agnostic to the optimizer at play. I think that, like, trying to cake this into the incentives is super important, Karim, because otherwise you'll always be forced to, be ahead of the game. Like, what is the best optimizer? Do you see what I'm saying?
Yeah,
like, you don't want to.
I get that completely. I guess also, I think part of it is I'll post a link to this podcast from the News Guys. Is they in part of this podcast they do something very well, and it's they ask us all to sort of reframe how we think about training, because when you think about it, we've all been programmed to train models on like a single node, single terminal, right? And there's a huge landscape out there for potential improvements that could supersede normal vanilla training if we were to reframe the problem and not think about it as it's usually designed, of a single node training. Like, it's kind of like we train at the moment using single node code, and we're trying to tweak it in so many different ways to multi-node, right? Even the idea of like syncing model states, and this is what I think they're going to be pushing for with their paper, right? Is why do we have to have a global single model? Why, like you say, do we have the single shared optimizer? Why can't we think of worlds where we have very slightly different models, but models that are in the same cluster, they're moving in the same direction? So I agree completely. It's all about reframing that problem and then trying to tackle it in a way to allow the smartest people to innovate instead of us being the limiter.
Exactly. And if you look at the history of machine learning too, like, one of the innovations in gradient descent was stochastic gradient descent, where they gave up the need for the nodes to produce the gradient on the entire data set. They were like, oh, you can produce a gradient on just a subsample of this massive data set, and that still is going to help us converge. Indeed, even further, it's going to help us converge faster. And I think that people have been daunted by this idea of doing distributed training for all this time, because, like you said, we're basically trying to squeeze the centralized ethos into a decentralized mechanism, and it requires like just a leveling up in terms of creative thinking to completely recraft the problem as for the decentralized environment, and thinking from the perspective of incentives, I think is almost always the right way to do it, because if you build a really cool, hive mind, for instance, Max Rabin, a fantastic guy, really intelligent, amazing technology, hive mind's stuff, and I believe it's the back end of what you're building, Karim.
Yeah.
Not built for incentivized computing, and it shows, right, when you're using it.
Exactly. Yeah. I mean, it can be. It's I think similar to, I guess, what the guys are doing at the Prime Intellectron is. I think all the experimentation is being done with trusted community members who are providing the compute. And so, yeah, like you say, it's all about the incentive problem and thinking about ways you can combat that. I think that's going to be the core, to be honest, of this. I mean, when you talk about papers published and things like that, I think that's where we're at the frontier, and what we should be publishing is, I think it's obvious we're at the frontier of like being in a space where we're applying this with a lot of money at stake. And so everyone's incentivized to break our system much more than anyone else's. And so we have to have the most robust validation mechanisms, and we have to lead that frontier.
Exactly. And if you, like, when we were designing Subnet 3, we always had in the back of our mind, okay, how is somebody going to cheat here? And that actually informs like the type of, optimizer that you're going to use, or the type of communication that you're going to use, and like whether or not you even try to have a synchronized optimizer or not, because you realize, well, if you can't craft it as an incentive, there's just no way that you'll ever make it work. And I think this is one of the problems with going the other direction. Like, let's just do a distributed training run where, like, hey, it's just me, you, and Autometa, and we like each other, and we can trust each other, and then let's put incentives on the top, and then things fall apart really, really quick. And so I actually think that, like, and I said this before in the call, it's like the holy grail is always, what is the way to craft the incentives so that they are in the direction of lowering or improving the loss of a model. And I just know that there's some mathematician that's going to have a lot of fun with that. We first have to give them a world and try this out before they even come to us, right? Because they can't test in production like we can, And what does it even mean? How can you even attempt to run an incentivized system in a research lab?
Yeah, defeats the point. This is the research lab. I mean,
this is the research lab.
Yeah, I mean, because you have to have people trying to break it. Even like we said this a million times, we keep repeating it. Even our own test nets, aren't a research lab to the sense as mainnet is a research lab, because you can try all you want to predict the hacking mechanisms, but nothing's as gold as what comes up live in mainnet. And that's, I think, what we're trying to prioritize in Subnet 38 is kind of having tracking mechanisms to be able to determine whether there's a weakness in the validation mechanism and to adjust accordingly, and to continually be trying to break your own validation mechanism. Exactly.
There's no better test than miners on Bittensor. I mean, a good point. We should probably try to incentivize the testnet. That would be fantastic, right?
Yeah. I think that would introduce it's about introducing. I mean, it's kind of what you were saying already with like asking me about emissions, right? Emissions is kind of like a dial of how much you want to like test your system. So in a sense that could be maybe reapplied in testnet in a way. The higher you up the emissions, I think the more people will flock in to try and break it.
Yeah. So
and
what's next,
the better your validation mechanism. I think for us, what's next is I think maybe that graph I was showing where key is really model size that we care about, and looking at some of the recent advancements out there in the field. So I know we mentioned the local a bit. So I think that's something for us we think is very high potential. Effectively, for everyone who maybe hasn't come across it, what the loco enables is that world I was referencing there, where we, at the moment, if you think about our subnet, everyone's running the same global model, right? And you can't diverge. What the loco pushes for is everyone to train their own models, but to have an optimizer that syncs between the shared average of all the models versus your model, and to sort of drag your model close to that global average of all the different models. And the beauty of that is, unlike what you guys are doing at S3, I think in Subnet 3, you're reducing the size of the gradients you're communicating each step. What this will enable us to do is reduce we'd still be communicating a quite a high percentage of the size of the gradients, but way less frequently. So in the Open DeLoco paper, they train on a standard like 512 or 1,000 batch size. That's internally, but they only update with everyone else every 500 steps. So you can think about it as kind of like an effective batch size of 500,000, which is humongous. It would enable us to train maybe at 2 or 3x faster speeds. So that's, for us, I think the next frontier is how do we shift our validation mechanism to enable it to adapt to a world where not everyone's not running on the same global state, but instead everyone's running on different model states. And we think that will help us grow bigger models, but it will also help this world picture you're painting, where it would then allow people to get creative and just improve their model. I'm visualizing a graph in my mind. I don't know if people can see it, of like, imagine clusters, and each cluster is like a model, and these clusters are like moving across a graph's axis and lowering down the loss curve. And you're trying to learn from the models closer to you in the cluster, and you've got the freedom to move as low as you want. And that's sort of the world we want to move to. And we believe that will easily enable, I mean, you can see the guys at Prime Intellect running a 10 billion parameter model that's each miner would probably be sharding the model across a number of GPUs. But I think that's doable with the great work they've been doing with their Prime repo, with a lot of work on how you shard models, how you share states. And I think for us, that's hopefully an achievable goal in the next couple of months.
Absolutely. And I will say, it's so much machine learning is exploration and then selection between things that have been explored, right? That's basically all it is. Random permutations until you get lower in a loss landscape. And so it makes sense that having divergent models that periodically come together and then select from each other in some sense is enough to lower losses over time. So Grim, if you were implementing DLoco, how would you do it as an incentive mechanism? Have you thought of this?
Yeah. I mean, naturally, we thought about it as like an upgrade from what our current system is, and so because also the aim is to sort of gradually grow into something better rather than shifting the entire subnet code. And so I think for me, the thought would be to potentially use some of the learnings you guys have achieved and gotten to with testing with Cont and the Subnet 3 that you've just released, and potentially allowing models to be miners to be sharing a compressed version of their models, maybe to S3 or peer-to-peer. We still haven't decided. I do like S3 a lot, given the benefits you've outlined, and to effectively be evaluating, so be dropping into each of these model states and evaluating how their version of the model converges, or how much of a loss their version of the model achieves versus other versions of the model. But that's the validation mechanism. The actual implementation of the technique is not that difficult. Their original release of Open DeLoco, so Prime for context released an open version of DeLoco, which initially their source code wasn't released, is built as a wrapper on top of HiveMind. For us, it's actually not that complex to enhance our current structure to include DeLoco. It's effectively just a wrapper on top of our optimizer, a very, very clean, well-built wrapper that they have open sourced. So we think there could be ways to do both, right? That's what we need. We need to update our system itself and the validation mechanism of that system together, and that will really boost up the space to jumping in terms of model sizes, because we'll be doing exactly what we'll be doing, but we'll only need to be all reducing every 5x steps of what we're currently doing. So we can afford to spend 3 to 4x longer times on an all reduce. So I think that's an immediate objective for us.
And it would be huge, Karim. I think we could actually push with something like dlocal in place on your subnet. You could push into the 10B and the 20B and the 30. And for the validators, talk to Coldent guys. They figured out how to run 20Bs on a single 4090. True story.
No way. Okay.
So you can validate.
Yeah, that would be.
Yeah, that's for them. Formalized. Anything you'd like to drop in here? Final remarks. Where are we going with Subnet 3?
Yeah, it's very premature, but we're looking forward to at least getting the baseline running, then accelerating. So come break it. We invite you to come break it.
Don't break it. Run some miners. Cool, guys. Yeah, this is awesome. I'll reduce the things. Absolutely.
Sure.
Automata, thanks for coming up on the stage. Appreciate you being here. Distributed,
Thanks
as always. Great, guys. Have a good night.
Bye.
Ciao.